So this is where we left off. We went through, first you graph all the forces, if you remember. So well, first you letter all the exterior and number all the interior cells. And the exterior's lettered between the forces, like that. And then you go from, first you do the forces, so you go from A to B, and when you cross A to B, you cross this 12. So you go from A, you make an A, and you go, and the 12, you have to pay attention to the direction too. This is going up. So that gets up, and then it goes down by 6, down by 6. As I cross each one of these, D to E. Oops. Come back. Bother. Okay. It goes 6 and 6, and then you cross these. And every time you cross, so that's why there's, we have to number the cells and letter the exterior things so that that's the way you designate each of these members, is by how it crosses, right? And I believe it. Well, yeah, we'll see in a minute. It's better if you cross in a clockwise direction. Like if I cross from, well, let me pick two that are going to be somewhere. Okay, these two. If I cross from 2 to 3 in that crosswise direction, then I draw this slope 2 to 3. That has an orientation, and that will show that actually does keep track, just like it had the orientation of the vector here up and down. It also has the orientation of the vector on the diagram. So let me show you how that works. I guess we can look at it here. Yeah, that's why I think this explains here. If you take a joint, say you do, after you've finished it all, so here's the diagram, and you can, and you can measure these, right? That's the statics graphic part of it. You can measure them and get the forces, just like you measure a force diagram, right? Okay, so if I do a little free body diagram, and I've got this is this thing down here, and this is B, and this is 1. If I cross from B to 1 in a clockwise direction, see if I do this right, and then I say, then I look up and I say in that direction, B to 1. So here I say B to 1. That means the force here is going in that direction, from B to 1. Okay, so that gives me the direction of that force. And if I go from, what was the other one down here, A, still going clockwise, right? If I cross from, now I'm going from 1 to A, right? So I go from 1 to A, and that's the direction of this force. So it not only has the diagram not only has the magnitude, but it also has the direction of these forces. You can read the tension or compression off of the diagram, which is kind of nice. Okay, and all these lengths, of course. Oh yeah, and this is from Dr. Frame. Did I send you that link? Did I post that or send it in an email? The link to where you get this program? How did I forget that? Okay, I'll do that after class. This is a very, very nice little program because it's just so simple to use. It is a finite element program, but they give you a graph, and you just from point to point draw it and put loads on it, and it immediately gives you a graphic kind of analysis, gives you the forces back on all the members, color codes it for you. So it's kind of nice, very simple to use. There's this one, it's kind of part of a suite. Then there's a one that's called Dr. Beam that does simply draws shear and moment diagrams, shear, moment, slope, and deflection diagrams for any beam. So you draw a beam, and it's very simple. You just draw it, label it, put these loads on it, and boom, it does all the diagrams for you. So it's I find it very handy. And the school has a license to it, and you can use it. Anybody can use it, really. And I'll send you the link to where it's posted on the school website under software. So I'll send you kind of a link, and you can download that and load. The only glitch is it only runs on PCs. It won't run on your Mac. Sorry, but it does run on PCs, and there are also copies of it in the BT lab downstairs. It's loaded on all the machines. I think all the machines in the school here, probably. Anyway, okay, that little aside. Now, the next thing is designing, right? And we started to talk about that. What you can do, these are called a dual. We started with this diagram and we created this diagram. If you alter this diagram, if I move the points around a little bit, I can go backwards into this diagram and see how it would then affect the shape. So there's a relationship, not surprisingly, between the shape and the forces in the members, right? So you change the shape of the truss, obviously it's going to change the forces in the members of that truss. Well, that's the beauty of this whole graphic statics is not, I mean, you could easily analyze, you could use Dr. Frame and analyze the truss. That's not the trick. But to go the other way is a little tricky because as far as I know, well, not the only way, but the common way would be just to alter the truss design would be just trial and error. You try one, you say, oh, well, I'd like to reduce the forces, and you just kind of trial and error to figure out a new design. Well, this gives you at least a method, a tool to redesign it. You can actually control the forces in this diagram. So if I decide, oh, these forces are kind of high, let's reduce these forces, I can simply reduce them. I can push the whole thing this way, right, is what I did, and it reduced the length of these. So where was it? 4D was 24, and I brought it down to 20. Okay, the price I paid is the truss got deeper. Okay, all right, maybe with a little bit of experience, you'd realize that you make the truss deeper and the chords are going to reduce because you're increasing the moment arm between the chords. But still, kind of an interesting tool. So, to show you how that works, I redid these diagrams the other day, hoping they'd be a little bit more visible. I guess they were on a black background, but okay, maybe this is a little bit easier to read. So here's an example. We'll start with this. This is the truss. It's got all these the loadings on it, and I drew this diagram based on that. So it's lettered actually a little bit maybe different. I started with the largest space and made that A, and then I came down here B, C, D, E. That's pretty arbitrary how you do this, but you just have to be consistent yourself. And then I numbered these 1, 2, 3, 4, 5, 6, 7, 8. Okay, so if I go from A to B, from A to B, I'm going up 75, so there's the up 75, right? That was the 75, and then I drop 50, 50, 50, so it drops 50 to there, 50 to D, 50 to E, and then it comes, when I go past that, it comes back up, and it closes at A. So, okay, that worked. And then I put all these, the slopes of each of these lines, right, matches the slopes of the actual members, because it is a force diagram, and it is an axially, what do you call that, two force members. So this is the diagram I got. All these are horizontal down here on the base, so that's the horizontal members there. Then these are I tried to color code them. So we go A1, where's that? A1, this member here is this member, right? And then the chord, so these are all the chord members. And then the diagonals are end up being these little pieces out here, right? So 1, 2, there's 1, 2, oops, 1, 2, like that. Okay, so I got that diagram. Now, I look at that diagram, and this is where I can start to manipulate it. I manipulate the force diagram, right? So I started with this. This is what I just did on the other page. And now I'm going to change it, so, right? This is changing it to hopefully make it better. That's would be your goal, I guess. And maybe a little bit arbitrarily, I decided, okay, I've got all these top chords. They're getting, pretty heavily loaded in the middle. Why don't I just try to make them all the same? They're almost the same anyway, but I'll make them the same. And that way, maybe the rationale would be, I can use the same piece to do the entire top chord, which, okay, maybe true or not, because of the different lengths, they're going to have different buckling factors. But okay. So what I did is I drew this arc so I could make them, with this as a center, made them all the same length. So that was what I picked as a thing to change. So I've made these all the same length, and now I just have to, when I change those lengths, the rest of the diagram just kind of follows it, right? You can't remove members, right? You've got to keep the same topology. So you got to keep the same number of members, and the connectivity between them, it remains constant. You don't change that, but you can change the slopes of them. You can change the position of these points. So that's what I did. I moved that around a little bit. Okay, now I've got to go backwards and see how that affected the original truss. So what I do, remember the slopes of these members are the actual real slopes on the truss. So I simply copied, and this works nicely in CAD. It's a little bit more cumbersome to do it by hand, but in CAD it's very easy because you can just copy and paste it. So I took A1, where is A1? Oh, A1's way over here. Okay, well, maybe I took A8. Let's say A8. I did half. Oh, and because it's symmetric, I only did half of it. Okay, just to save a little time. Okay, so I took this side, A8, A8. Here I copied down to there, right? So I just literally copied it from the diagram and pasted it onto the original truss. And initially I just paste them all at the center points, right? So I take each of these and I copy them down here, and I just copy them onto the center points. And you can see, okay, they're pretty screwy. They don't line up initially. I can, to make it a little less confusing, I went through and I deleted out those original members. So all I have are the new members that I copied down from the force diagram. So here, I'm only going to do half of it, right? So this is the old side here. This is the new side, right? And now the trick is I've got to make that fit together, right? I've got to keep the slopes that I've got there. I can't change the slope. And I've got to make them all fit back into a truss, right? And you can see initially they're not. I mean, these joints aren't coming together. Well, you've just got to go through, and the best way to do it is just go through one cell at a time. You pick one cell, 3 corners, and make all those match. And you can move, in playing that game, I can move these around, like okay, right now, those two and this one, they're not coming to a point. They have to come to a point. It looks like these kind of did, and these did. Well, if I take this bottom one here and just slide it upward, right, I can eventually bring it to that point. So I can move this, right? I could move it upward, and then it would still have a point there. It looks like that made a point, and now I'd have those 3 crossing, right? So you can shift them around. That's the game. You shift them around so that you get 3 points crossing. Okay, so then that did it for that guy. That gives me one cell, right? So I've got these 3 points crossing. And in CAD, it's a little bit easier to tell when you can precisely make them cross, right? Okay, now you look at the next one. Maybe initially, it looks like I already moved it down here. Initially, these were not crossing. So I could take, this, whoops. I touched the edge and it makes it go crazy. Okay, there we go. So I've got this one. I moved this up, so we got that crossing. Now I'm going to have to, I've got, once you move them, it kind of locks that point. So these 3 points are locked. So now I move to the next cell, and I could move that up maybe, and I could move this down so that those 2 would cross there, right? And that would give me this and this and that. So I think that's what I did here. I moved this one up, and I moved this one down. And you can move them anywhere, you just can't rotate. You can't change the slope, you can just move them. That's your only possibility. Okay, so I got that one. I got it up there, and now this is not, well, I guess it crosses with that, but it's not this one. Holy smokes, that's supposed to cross down here. So I'm going to have to move this way over there so that I get this somewhere. This is coming down here, right? It's got to cross with that. And then this has got to be moved over there so it crosses. So so that's how I ended up with this being shoved way over there, and those 2 come up then. So again, you just slide it until you get another cell. So I started over here, and I just went cell by cell, making 3 corners cross. And once you get a cell finished, then they're locked. Okay, you can't move those again. Once I got this cell finished, once I got that point, I can't move that point again. So you can only, that's why I had to shove these way out so that they'd cross. Okay, you could come, all right, so that finished this one. Of course, it's symmetric, so the other side would be the same. I started over there in a corner. That was kind of arbitrary. I could have started up here at the top. I could have started anywhere, really. It's just wherever it's convenient. But once you get a cell finished, you have to kind of keep track of, that's why I was putting these dots on it. That locks those points. And once you get one finished, you can't change it. Or it just screws it. Then it's not working. Then you gotta go back and change it. So you just have to start somewhere and work through it one at a time. This was the the Dr. Frame analysis that shows, yeah, I actually did achieve that. The top chord, for what it's worth, is all the same. Right? I ended up with an enormously long top chord up here, which is then maybe not going to do too well in compression. But at any rate, it's all, I mean, I achieved what I was trying to do there. And this just, let's see, I could have started, I think here I started up at the top maybe. You can start at different places. It can come out to be different scales in this. The scale of this drawing is not the original scale. It can change size, right? And that really doesn't have any meaning. You're not trying to preserve the scale in terms of feet. You're trying to preserve the slopes, right? You're just trying to get the geometry. So what you do is, once you get it, right, then you know what the length was that was supposed to be, and you can just scale it to the proper length. It'll, right? It just scales. But it gives you the correct shape, and you could change other things. Obviously, I guess in this last one, I was looking and I thought, well, this is kind of dumb that on the end it has a slope. The bottom chord was not flat, so I went back and you can change that. You just have to, this was going, I think it was going up like that, right? And I just moved this point down to there so that would be flat. So you can introduce constraints both in terms of slope. In the force diagram, you can control the slope. You can also you're controlling the lengths of those members, so the lengths represent the forces. So yeah, I can go back in, if I notice that wasn't flat, I can flatten it, and then it'll come out flat. That actually reduced the center a little bit, which is probably better too. Okay, so you see how the game's played a little bit? You think you could do it? Yeah, I think you could do it. Okay, good. Give it a shot. Try to work through that. Probably, you can get a piece of graph paper and try it, but to be honest with you, it's much, much easier to do in CAD. And, just bring up a drawing of it, because then you can just move pieces around and it becomes a little bit easier to do. So go through it, make your initial force diagram of the one that's there, and that should be, I didn't actually make the force diagram, but you should give this I already worked out the forces on that, so you should, as a check, you should be able to match these forces, right? Because that's coming from this diagram. So you might, to make sure you know what you're doing, you could try it, and then in CAD you can measure the length of those members, right? And the lengths of them in the force diagram should come out to these forces, right? Should give you the forces. So you can check that with this. When you do it, then you change it, and your altered version you can record here, and then you can compare the two, right? To get the weight, you have to actually get the member, right? And that's why I ran this sheet off, just so you don't have to be trying to calculate every member. And there's these sheets, there's tables very similar to this. NDS makes a thing they call the manual. Should be on Canvas, I think. I probably posted a copy of it. And they have tables similar to this that are just sort of shortcuts to quickly picking the members. Same as a steel manual. They're probably trying to copy the steel manual. Well, the tables aren't quite as wonderful as the steel manual tables, but okay. You can pretty quickly pick a member, and that's at least it calculates CP for you. So these are for 4x dimension lumber. Looks like everything's Doug fir. I guess that's what we're using, I hope. Yeah, Doug fir number 2. So these are all for Doug fir number 2. All the 4x4s, 4x5, and so you've got to have the length. Here's the length of it, and the wood and the size. So I've got the size. You've got first find the group that's like for the size you want. So if I want a 4x6, it's down here. This is 4x6, and then I've got to pick the right length, and then I can read across. Once I get the length and the member, I can read across and see what the load capacity is, right? So you can go, if you've got the load, right, you can read this table and find the load and read it and find your member. So you should be able to use this to quickly pick a size for the member, right? And then you can, once you get the size of the member, it should give you, maybe it even gives you on here the weight of it, does it? Yeah, it does. Look at that. It gives you the self-weight. So you don't have to do a lot of calculations. Between this table and your graphic statics, you should be able to design it and get the weight. And the kind of the goal of the game is to get one that's a little bit lighter maybe than 676.6 pounds, right? So you can see if you can do that. And then I'll make a, oh golly, I guess I'll have to set up a thing on Canvas, and you can turn it in on Canvas. And this, I guess, I mean, it shouldn't take too long to do this, to be honest. But we'll wait. When's that STAD thing is due? This weekend? Is that what I put? I think I put the 19th. 19th, yeah. So if you can get, if you've been working on that, did that? Okay. Hopefully you're able to, if you have any problems with it, for heaven's sakes, let me know, and I can try to help you. I mean, don't waste a lot of time, if something didn't make sense or work. I can try and, the best thing to do would be to send me your STAD file, and then I can see usually I can see where the mistake is and correct it for you. But yeah, so try and get that done this week, and then if you have time this weekend or whenever, you can do this, and we'll put that. Oh yeah, here you go. Sorry, I forgot to give you that. Right. So maybe this will be due the week after. Is that still March? Maybe. Okay. All right. Okay.
Peter,
Yes.
how do we upload the files, stat files, the PDF and?
It should be on Canvas. If you go to Canvas,
Oh, okay.
it should now be open. It wasn't maybe last week, but I did open it now. It's hard for me to tell, because although I see a student view, it doesn't always, I can't do it myself, so I'm not sure what you see, but I'm hoping. Is it open?
Yeah.
Okay, it is open. So there should be in STAD an assignment or something, and it'll allow you to upload 2 files, the PDF of the report and the STD file, which is the STAD input file. Those 2 files is what I'd want. Okay, so, right. Now, that should be that. Let me close this and open this. Next topic. Oops, hit the wrong button. Is it up there? Yeah. Oh, my favorite painting. This is my favorite artist, Caspar David Friedrich. When I was your age, I guess, I don't know, how old are you people, 20-something? When I was 20, it must have been 21 or 22, I forget. I got a internship in Hamburg, and I got to spend the whole summer in Hamburg, which was lovely. It was really nice, except I didn't speak German. It was the only drawback. By the end of the summer, I spoke German. But I learned a lot of things. It was really quite a summer. I ended up getting engaged that summer. It was pretty eventful. But there was a museum there in Hamburg, and I used to go there every, I think, like, whatever it was, Thursdays it was free. So I'd go every Thursday and spend the whole late afternoon, evening going through this museum, and they had a whole collection of Caspar David Friedrich. Lovely. I mean, I just fell in love with that Renaissance, not Renaissance. Yeah, look at this. I even forget the name of it. His style of painting, which was late 1700s, I guess, 1800, early 1800s. Okay. Impressionism? No, what was it called? Realistic something. Oh, okay. Anyway, they're actually, and this is just a clip of it, and I took it because the tree here is leaning. So obviously the tree would be in compression, but because it's leaning, it's also in flexure, right? It's a little bit of a cantilever. So that would be, that poor tree is under both compression and flexure. And the Mann und Frau, that they're not really looking at the tree, they're den Mund betrachten. They're standing over here to the side. I cut them off. Anyway, okay, so we're going to talk about these combined forces. There's a whole little section in the NDS that we kind of skipped over earlier. Is it chapter 3? If you go in here, chapter 3, probably a little past that. Oh, solid columns. No, I think it's toward the end. Ah, here we go. On page 22, it starts first with a 3.9. Is that what I got here? 3.9 combined bending and axial. It starts first with 9.1 is bending and axial tension, and then 3.9.2 is compression. So they, first we'll look at tension. That's a little bit easier, and then we look at compression. So here's the. I still got my. Somehow I lose my pen when I. This would be the combined tension. This might be, where would be a tension member? These bottom chords of this kind of truss situation here are certainly in tension. And if you've got something up in your attic, it might also be in flexure, right? So that would be tension plus flexure. These guys on the side, they're definitely in compression, right? Oh, wow, my pen doesn't. And if they've got a wind load on them, then they'd have the addition of flexure. In tension, they just consider one axis. I guess they decide is enough. In compression, you could either look at it flatwise or in the normal depth ways, like that, edgewise, I guess is what they call that, flatwise or edgewise, or a combination of both of them. So this is what we're talking about here. And the in 3.9.1, they talk about the tension, and there are two cases, what do you call those, scenarios or something that you could have with tension and flexure. And this would be either where you've got the top one would be tension critical. You've got more tension than flexure, so you've got a lot of tension and a little bit of flexure. That might be that attic floor, really. It could be potentially in considerable tension, particularly if it was under a heavy snow load or something, and then maybe you just have a little insulation in your attic, something like that. So it's not so much, there's not much of a load beyond dead load on it. So that would probably be tension critical. The other option would be I used to store engine blocks in my attic, which was a little bit dicey. And that was pretty heavy load, and that would have caused maybe more flexure, and it would have been more flexure than tension. The flexure would have been critical. So these two formulas then reflect those two different scenarios, and you can see it's mostly a ratio. When we take the actual stress over the allowable, right? And you've maybe seen this in the steel manual. Seems like I've seen this formula somewhere else before. For combined stress, you're essentially taking a percentage of that stress, right? You're saying if this was in a ratio of maybe I don't know what would be half, 5 to 10. I don't know what those in kips maybe, or KSI or something. Anyway, some ratio that would come out to be 0.5. Man, can't draw. And if this one was similarly 0.5, they'd add up to equal 1, and that would be represent 100% of the stress capacity, right? So you're taking it by part. You're saying, okay, the tension here could carry a certain percentage, the flexure could carry a certain percentage. They can't carry more than 100%, right? Which also means neither one of these could be over 1, right? If you go over 1, that would mean the allowable would be greater than the actual would be greater than the allowable. So neither of those pieces could be over 1, and even the sum of them cannot be over 1, cannot be over 100% of the capacity. Okay, down here, okay, it's a little bit different. We gotta subtract the tension from the flexure stress. Essentially, what I have a diagram of that in a minute, yeah, and that gives us a proportion that would be where the flexure is controlling. Okay, these asterisks here in bending up there, we can because it's in tension primarily, we don't have to worry about lateral buckling because it's primarily being pulled. So if it's being pulled, it's not going to buckle out laterally. So you can skip that. Down here, you really should include the CL. So you should have, plus CL here. But they say you can leave off the volume factor for some reason. That's only applies to glue lam, right? Is where that volume factor comes in. Okay, so this is diagrammatically how these work out. If I've got a tensile force, right, and a bending force, and I add them together, they can add if the tension is greater. If the tension is greater than the bending, then I'll end up with this. This would be where tension is critical, right? That would be this first formula. So that should be that one. And here, if the compression due to the flexure is greater than the tension, then I end up with compression up here, right? And if I have that compression, then I've got to consider the lateral buckling and whatnot, and that is what that formula is supposed to describe. Okay, so that's why there's the two formulas. Okay, so an interaction diagram, maybe from what is it? Concrete. You use interaction diagrams, don't you, people? If you're familiar with concrete, I can remember textbooks that had a dozen diagrams, and you could actually use the diagram and see whether if you fell in here, you'd be safe. If you got outside the curve, you're unsafe. So the interaction diagram is pretty simple. In this case, you're just a straight line because it's just the sum of these two. That's the interaction of the tension critical formula. So Yeah, if you'd go from pure tension to pure bending is what that's doing, and that in between. But we don't really use the interaction diagrams to. I mean, it's easy. The formulas are so easy. I guess it's easier just to do that. Okay, so axial compression. This is the other one. This one's a little bit more involved, as you see. Formulas are a little bit hairier. And we've got compression here. That's this easier part, right? The ratio of the actual stress to the allowable. For the bending, it looks at bending on two axes. Okay, they call this edgewise, I believe. Edgewise. And this one is the flatwise. Flatwise, whoops. Flatwise. And that would be, this is the edgewise, this is the first one, right? On the edge, and this is the one that's on the flatwise. So you you probably don't have both going on at the same time, to be honest. I mean, that'd be pretty weird if you think, what would be that? I don't know. I guess there would be a scenario where you might have it, but not very often. Usually you have one or the other. And if it's flatwise, then you just leave off that part of the equation. If it's edgewise with no flatwise part, you leave off the bottom part of the equation. So you just use the part of the equation that applies, right? And the other part would just be 0. There would be none, so that would be 0. And you've always got the compression aspect. Now, it's kind of interesting the way this formula is worked. If you see, this is just the ratio again, right? That's this same ratio of actual stress to allowable stress. And then they multiply it by a factor. That's supposed to be a 1. Okay? And they call this factor that they multiply it by, you can call that an amplification factor. Okay, amplification factor. And that accounts, what that's doing, it's accounting for a P delta effect. So when I have, I forgot to bring my little rubber beam up here. Well, if this were a column rather, and it has some load on it, a flexural load, it'll bend it a little bit, right? And the force is coming straight down it, so the force is actually offset by some delta distance from that center point. And that offset then causes a force times a distance. It causes a moment, which means it bends even more. And as it bends more, it deflects more, and that can escalate and cause it to failure. But at any rate, you have to account for that extra bending. And that's what this little factor is doing here. You can see a little bit, if the compression gets bigger, then this denominator gets smaller, which means the factor gets bigger, right? So the bigger you make the compression, the bigger that factor amplifies the effect of this stress here, the edge flexure on the edge. And the same here, the amplification factor just looks a little different. It's a little bit more complex, but it would be that, right? Oops, with a 1 over it. Okay. Now, if you look in here, there are these ratios. You just have to make sure those ratios don't go cause the amplification factor to suddenly go negative. Those ratios have to be less than 1, right? If they got greater than 1, they'd be like if they were a negative 2, a 2, then they'd be subtracting 2 from 1, it would come out negative 1. So that's not what you want. These should always be less than 1, and I think they say that here somewhere, right? Essentially, that's what this is. I think that's what this is about. These have to be that's what's making that so. You have to have these actual stresses have to be less than these other stresses in each case. So all three of them. And they apply, all this is saying is they apply where they are there. Okay, like that. Okay, so, and of course, the actual stress for compression is just P over A, and for bending is M over S. So that's pretty straightforward. Okay, so this is the way that would be, these equations would be used for, right, this is compression plus flexure in the X direction. This is, I mean, the normal, how we call these. Strong axis bending would be X, right, and weak axis bending would be Y. Well, they don't like the X and Y nomenclature in wood. I guess they don't because if you use it flatwise, it is rotated, and maybe that they thought was confusing. So they don't use X and Y. They use this D1 business. They're talking about that direction, the strong axis, and D2 is flatwise. That's the weak axis. Anyway, so this would be strong axis flexure. This would be the flatwise, and this would be a combination of them both. So you can have any of those three. And actually, I wrote these up here, but this one also applies, right, that's B1. Yeah, this one also applies up there. And they both apply, I mean, this one down here. So they apply wherever they are in the formula. Those limitations apply. Okay, as far as the interaction diagram, yeah, because of that, I guess the amplification factor, the slenderness makes a difference, so you get slightly different curves. It's not just a straight line, depending on your slenderness. So Breyer puts these illustrations are all out of Breyer's textbook. And he gives those interaction diagrams, but like I say, they're never used. You don't, except for just to look at it and say, okay, interesting. That's what that is. This just mentions the P delta effect, has a nice illustration of it. So this is the delta due to presumably some lateral load causes that initial deflection. And then when you load it, you've got the load times that distance, right? There's some offset distance, and that causes an additional moment, and that moment is what we call, golly, what is with this? I guess because I use it, I'm not holding it straight. No, it still does it. All right, that moment is P delta, P times the delta distance, and that's what this amplification factor is accounting for. It's increasing, so the greater your, I don't know, the greater the buckling factor increases it, or greater the compression stress. I guess the greater the compressive stress increases it. Anyway, that's the factor. Okay, so that's the amplification factor, right? Okay, so examples where these occur. Trusses is a good example because you've got here we'd have axial compression, right, plus the bending. Here you've got axial tension in the bottom chord plus, however many engine blocks you got up in your attic with flexure. Of course, in frames, the frame's a little bit less for a wooden structure, right? Because you don't have fixed joints usually, but you do have continuous. At least you have continuous members. Well, I guess this diagram's about right because you don't have any. You have wind load on the exterior columns, and if those are continuous beams on the interior, okay, so you'd have bending and from the wind load, maybe you'd have a little bit of compression there. Okay, maybe. More likely, you've got situations like this in wood, where you've got a beam tying into it, and it's not not a concentrically loaded column, right? So I'm loading this column over on the edge, and then I've got some eccentricity here, and that causes a bending moment. So that would be compression plus the moment due to that eccentricity. Or here, this is with the wind load on an exterior stud wall or something. I think that is, if I remember right, is the homework problem that's based on this, which is this week's problem, I believe, is this case, is a stud wall with a wind load on it. Okay, so see if we can get maybe through this example. This is an example that was based on one that is in Breyer's textbook, although I don't think he did the chord. I think he just did the bottom chord. He didn't do the top chord. I went ahead and did both chords, so we could look at an example of tension down here and compression up there. So I'm going to look at the we'll go ahead and do an analysis of the bottom chord here and an analysis of the top chord, and both of those have a uniform load placed on them, so they've got flexure in them, and they've also, as a truss, they've got axial force, so you've got the combination. And we'll use this material, hem fir. Sorry, we haven't had a wood of the day in gosh, what, a whole week, 2 weeks? It's because I feel like I'm behind. I'm trying to catch up. We'll get back to wood of the day. Don't worry. Maybe next week. Okay. So what do we got here? These are supposed to be 4 foot on center, right? So there's another one over here at 4 feet on center, and the span of the whole thing is 30 feet. That's what that is. And the load is given in PSF as a roof load. So if they're 4 feet on center, that PSF times 4 should give me these loads. So if I say this plus this is equal to, looks like 44 PSF times 4 feet should be what that is. Does that look right? 4 times 44 is maybe that's where I'm getting the loads. So that's just an explanation of where these loads are coming from. And in the attic, it's 8 feet. So as a dead load, 8 times 4 should be that 32. Okay, so those are the loads that are on it. The bottom chord we're going to say is a 2 by 8, and the top chord is a 2 by 10. Okay, that sounds pretty reasonable. I'm going to also assume that particularly on the top chord, that I've got the sheathing nailed pretty close together, so that I don't need to worry about CL because of the sheathing bracing it. So although for compression normally you would calculate CL, I'm not going to do the CL because I'm going to assume it's braced. Okay, so determine the joint loading. Yeah, okay, well first I take this load, right, and I divide it up. These are 7.5. The bays are 7.5 feet. So I think this from center to center is 7.5 feet. So 7.5 times that PLF load should be that, right? That should be the 7.5 feet times 100 and, well, let's put it into kips. 7.76 kips per linear foot, and that should be that then. Okay, so that's where these point loads are coming in. This is half of it, and this is the load from this is from the roof. I mean, from the ceiling, the attic floor, or whatever that is. So this is the dead load. This is the dead plus snow. Okay, and yeah, that's the end reaction of, and I'm going to assume it would be held by that, right? So my span of the bottom one is only that 15 feet, right? This is 15 feet. Okay, so we got all those. We can go ahead and get, based on that, do a little free body diagram and get the axial forces. So the axial, well, let's see, I added these, right? And that's going to be that load. And then if I subtract that from that, I'll end up with that, right? That's summing the vertical forces. And then using this as, I think, what was the height? I think it's 1 to 2. Is that 1 to 2? Yeah, must be 1 to 2 slope there. So if this is 222, this is 444, and that then these are the only two horizontals, so that gives me that force, and then the resultant of those two would be this. All right, so I've got, that just gives me the forces from that little corner, and these are the two that I want. I want that for the tensile force, and I want that one for the compressive force. So we'll do the tension member first. Here's a diagram of the tension member. This is the bottom cord here, right? That guy. It has a flexure load on it up in the end. Actually, just the dead load is that 32. Although it only has the dead load on it in flexure, this load is coming from the snow load. So in terms of a CD, I'm still going to stick with the snow load, which is what, 1.15 or something like that. So I'm sticking with the snow load. I mean, the whole problem has got the snow load on it, so that's going to be my CD for everything, is based on the snow load. If the snow load went away, then this would get to be less. That was a scenario. You know, my attic with all the engine blocks in it, I realized that I had put them up there, the last ones, in the winter, and there was a snow load on the roof. And it occurred to me, oh my gosh, what if spring comes and the snow melts and this force becomes less? Suddenly flexure would control. My whole ceiling would collapse, but fortunately it didn't. Okay, all right, so we got those. Here we've got, what do we do here now? Here's we're going to look at the tension force. This is the, I want to see, yeah. Okay, this sheet, I just confirming that dead load plus snow load controlled. Okay, because there are two load cases. There is a dead load plus a snow load, and then there's a snow load with if the snow melted, would all my engine blocks suddenly be critical? And in this, I was able to show they were not. So this is, and the way you do that is you take the force and divide it by CD, and it gives you a factor, that. And you can compare that then. So you're just dividing out the CD to see which is critical. So here the CD for the snow is 1.5. If I take the PT without the snow on there, I leave the snow off. This is only dead load alone. That's what that is. So I just reworked the whole thing for dead load alone. And of course, the tensile force is quite a bit less, but my CD for the dead load is less. But then you compare these two numbers and you see which one controls, and it looks like this one does. right, by quite a bit. So don't have to worry about the snow melting and the attic being too heavily loaded. Snow load controls. Okay, so then we go on. All right, with that little aside. The bottom chord is a 2x8, and we've got two formulas, and the easiest thing, there's pretty easy formulas, rather than trying to determine which one controls, just work both of them. And they both have to pass, right? So to do that, there's our tensile force, right? That's going to be the tension, and I put it into pounds. There's the force in tension, right? That's tension. This is a 2x8, I guess, the area. So P over A gives me that tensile. The other, I guess the aside here, the thing that I'm kind of ignoring, it depends how that truss is built. Most trusses have a gusset plate, gang nail makes these lovely metal plates that just press on, and that doesn't reduce the area at all, right? They just press in there. You could, on bigger trusses, maybe cut a hole and bolt them together, right? That would be an option. And you might do that with, what did we look at? Those split ring connectors. Those are used in trusses. If you do that, you just have to be careful. You've changed the area, right? You have to use the net area. Because if you start cutting holes in it, or notches or anything, you got to use the smallest area. So that is the net area. Anyway, okay. Assuming we got that, ours maybe is gang nailed. We don't have to worry about it. Then we look at the flexure. Here's the moment, WL squared over 8. This is our 32 PLF, right? And we get that in terms of foot-pounds. This is for our 2x8, is our section modulus. So we can do the M over S. We got to convert it. So we had by 12, so we get inch pounds then, right? Is what that's all going to be. And divided by inches. And that gives us the actual flexure stress. So we got the actual tensile stress, 408, and the actual flexure stress, a little bit higher, 800, 21, 22. And now, I'm not going to do CL, well, in the attic anyway, I don't know, I think it's going to be tension. If it's tension controlled, if the first equation controls, you don't need CL anyway. I said this, although I think I'm kind of fudging it a little bit. I was looking at this the other day and I thought, I've always looked at that. This is from 4.41, where it says where you don't need CL. And I was thinking, I've always looked at that as, I guess because the ratios were are integer numbers, I thought, well, they must be doing this with nominal dimensions, like 2 or 8 divided by 2 would be 4. But then I was trying to prove that, and I was looking all through the code to find somewhere. They don't say it. They don't say it. They just say D over B. But if you look in the definition of D's and B's, they use D and B for both nominal and actual. So it's very confusing. And being confused, it probably would be the better thing to take the more conservative. So I don't know if this is really, I don't know if I'm saying that right, that the dB is 4. I think it's really, if I did that with actual dimensions, it would be 4.8 or something. I did it this morning, which would then not pass this, but okay. We'll say it's somehow, it's not critical anyway if tension controls. I think tension does control in this case. Okay, so let's see where we go. We've got these. So I'm not going to use CL. we've got for tension CD and C. Well, I used CL as 1. I guess I did write it down here. Hey. For tension, we've got CD. CD is for the snow load. CF, we got to look up in this table, right? For CF, for bending and for tension, they're two different numbers, but it looks like they're the same number, 1.2. So we got that, so we can get the tension pretty quickly. It comes out to be, it looks like 1,000, right? 1,000, you might check, make sure it's bigger than the actual tensile force, so it is, so that's okay initially, even when they're not combined, it's passing. Here CD is again for snow load. I said I'm not going to worry about CL, and CF is from over here, so I got that. 15 is greater than 8, so we passed that one too. Now we got to combine them. Okay, combining in tension. Okay, right, we had these two scenarios, right? So the first one is simply this. This is the first equation. This is the F over F, right? And we get these two ratios, and it comes out to be, wow, pretty close to 1. If it went over 1, it would fail, right? But we've got 5% leeway there, so we do pass. So that one's good. Then we can check the other one for, would be where flexure is critical. We get these same, this is the FB, right, minus FC, I think. Is that where that, FT rather? No, T. Over FB without CV. Well, we don't have CV anyway, so this is where maybe you'd have CL in there, but okay, so we got that, and that comes out pretty low, so it looks like this is the one that's really controlling, is the higher. This is only 0.27, so that passes. So they both pass. So if they both pass, then the whole thing passes. So it passed tension, it passed flexure, and it passed the combination of them in either way. Okay, so now compression. This would be this. We're going to look at this guy up here, that member, and here we've got a compressive force. Oops, I should say that's in kips. Of 4.96 kips. Okay, so that would be 4,960 pounds. I'm going to work it in a projected form since I've got projected load anyway, so I'm looking at a beam that would be a projected length, which is where this 7.5 comes from then. And then we got to figure out the flexure, right? There's the load that's on it, that 176 PLF. It's 7.5 projected length, so there's my moment. This must be for the 2x10, I think is what this guy is. And now we can look at the actual stresses in compression, right? It's just P over A, so we got that. And in flexure, it's M over the section modulus, so this gets it into inches, and we get that. So those are our two actual stresses. And then we do have to calculate a CP. You can't get around that, I guess. This just calculates a CP for a, and here you can't do it on that 7.5. You've got to use the real length because that's the length that would be buckling, the true length. So I've got to find the real length of it between those nodes on the truss, and divide that by the depth of the 2x10, and that gives me this L over D, which then I plug in down here in the Euler equation, and we get the Euler stress, And then we've got to, that goes into the equation. It's actually a ratio of the Euler stress to this allowable without CP on it, right? So we get that. There was the FC, and this is the snow load CD, and this is, what is this? That must be this. The CF, I guess, is what this is. That's CF for compression. And we get that ratio, and you remember the CP formula was that longer formula, but it's just a series of this ratio mainly divided by this C constant, which for dimension lumber is 0.8. Okay, so we do that. We come out with a CP of 0.89. That gets plugged in here, right? That's that one. There's the CF for compression is 1, and this was for the snow load, the CF, CD. Okay, so we come out then with an adjusted allowable stress, and we can check it against the actual stress, and it looks like so far so good. And then we can, that was the compressive side, now we can do the flexure. The flexure, again, we got snow load. I'm going to assume that it's braced, right? This is braced by the roof anyway. That makes sense. I think that probably would be true. You have enough sheathing on there. That would be braced by the sheathing. And this would be CF for flexure. Make sure you get the right CF for flexure. Okay, we got that. And multiply those, and that gives us an allowable of 1392, and that checks against the, whoa, man, that's supposed to be an FB of 69.4 that we just got on the other page. All right, that's the M over S. Okay, so those pass that. Now we have to look at the combination of them. And the combination, oh golly, what do we got? There is no YY, there's no flatwise bending. It's just this flexure and compression. So these are the two formula. I mean, that's the formula that we want. This one, the first part is easy, right? We've got those two, the ratio of them, and squared. It gets squared, so it reduces it a bit. And then the flexure, I can do, what I'm going to do is this part first. So that's what this is. Okay, and that comes out to that ratio. That's almost 0.5. And then the amplification factor I did last. And that comes out to be, and you can look at this, it should be an amplification, right? It should end up amplifying it. It shouldn't be less than 1. It shouldn't be decreasing it. It should be amplifying it. So 1.1 is amplifying it by about 10%, right? So that brings us up to 0.5. 0.55. Okay, you sum those then, this one up here and this one down here, and we get 0.6. Okay. Easily passes, no problem. So that takes care of that one then. And the last one, I think the next example would be this one, and this is the one that's actually this is, if I'm remembering right, this is pretty much the example that's the homework problem this week. And with 4 minutes left, I don't think we'll get this one, but we'll do this one Thursday then, I suppose. We'll slug through it. But it's pretty much the same. It's looking at flexure, right, due to the wind load, and compression due to, I guess, whatever's on the roof. Something's on the roof. And so we should not have flatwise bending. I don't think that's in this. It should, again, just be these two. Right, because the bending is being loaded like that. All right, so we'll pick up there on Thursday. See what you can do. You can make sure you get the STAD done first. Make sure you get that wrapped up and uploaded, and then you can maybe play around with the graphic statics. That would be something fun. And then we'll do this on Thursday. Okay, have a good middle of the week.